Okay, so now moving on to section 9 of chapter 19, we're going to talk about the controls that determine the flow of blood through our tissues. We have two types of control. We have intrinsic mechanisms as well as extrinsic mechanisms. When we're talking about the flow of blood through our body tissues, that is referred to as tissue perfusion. And tissue perfusion is involved in helping deliver nutrients and oxygen to all the cells that are making up the tissue, as well as removing waste products, so things like carbon dioxide or nitrogenous waste. If we're talking specifically about our lungs, tissue perfusion is involved in exchanging of gases, picking up oxygen, and dropping off carbon dioxide. If we're talking about our digestive tract and our alimentary canal, it's really important for absorbing nutrients and getting it into our bloodstream. We also have some tissue perfusion when we're in regards to the kidney, whose function is really helping in the formation of urine. So the rate of flow to each tissue and organ is almost matched to the exact amount that it actually needs, not really any more or any less. And the reason why we can match our blood flow to the tissue needs is because of these two control systems, our intrinsic controls, which are also referred to as autoregulation, as well as our extrinsic controls. So if we're talking about extrinsic controls, really the sympathetic nervous system and our endocrine system are going to be the ones that are controlling the blood flow through our entire body. And our endocrine system is basically made up of our glands and our hormones. And how do they function? They act on the arteriolar smooth muscle to help constrict and reduce flow to regions that need it the least. So if we dilated all of our blood vessels in our body at once, our blood pressure would fall substantially and we wouldn't be able to pump the amount of blood that we needed to critical tissues such as our brain. If we're talking about intrinsic control, again, also called autoregulation, the blood flow is adjusted locally just to help meet the specific tissue requirements. So those local arterioles that are feeding the capillaries can undergo modifications of their diameters so they can constrict or they can dilate arteries based on the tissue's needs, and again to help maintain our mean arterial pressure. The organs can regulate their own blood flow by varying the resistance of their own arterioles. Basically, the rate of the blood flow to each tissue or organ is, again, almost the perfect amount it needs in order for it to function. So, talking about the intrinsic versus extrinsic controls, if we're talking about intrinsic, we're talking about control from the tissue or organ itself. And they use things called paracrines, which are just local acting chemical messengers, or even properties of muscle tissue, so their ability to constrict or dilate. We already talked about how this is also referred to as autoregulation or local control. Extrinsic controls, we're talking about control from outside of the tissue or organ. And what we use is nerves or hormones, which are a part of our endocrine system, in order to control the tissue perfusion to these different organs. So just showing you how we can redistribute our blood flow and blood volume in the event that we were stimulating our sympathetic nervous system. So for example, during exercise. So at rest, our skeletal muscles only receive about 20% of our total blood in our body. But if our sympathetic nervous system is activated and we're exercising, our skeletal muscle can receive up to 70% of our blood volume. And how does it accomplish that? Again, we're going to be redirecting blood from tissues that we don't need during these situations. So for example, our digestive system, and then redirecting the blood to the tissues that do need them based off of our environment. So our skeletal muscle tissues in this case. If we're talking about which controls are at play, well, both. So we have our intrinsic controls that can act locally at our skeletal muscle arterioles and help them dilate. And if we are dilating our local arterioles, we can increase that blood flow to that skeletal muscle. Our extrinsic controls are going to act to help decrease the flow to other organs, like I mentioned, so our digestive system and our urinary system or our kidneys, helping to maintain that mean arterial pressure despite the dilation of the skeletal muscle arterioles. So intrinsic or local regulation, also called again autoregulation. So the local conditions regulate the blood flow, and that's independent of nerves and hormones. And how do they accomplish this? Again, by modifying the diameter of local arterioles that are feeding into those capillaries for that tissue. There's something called reactive hyperemia, and this is increased blood flow to an area due to these intrinsic factors. We have two types of mechanisms under our intrinsic regulation, and both determine final autoregulatory response. So we have metabolic controls and myogenic controls. Metabolic controls are our chemical controls, and myogenic controls are physical controls. But generally, both determine the final autoregulatory response that we're going to have. So let's first talk about the metabolic controls. So increase in tissue metabolic activity results in declining levels of oxygen. If we're increasing the metabolic activity, we're increasing the usage of ATP, our body's energy currency. In order to produce ATP in our mitochondria, we have to consume oxygen. It's considered aerobic respiration. So as we use all of that oxygen to produce the ATP needed to supply that specific tissue, we're going to have lower levels of oxygen. In addition, we're going to see an increase of the metabolic waste products from also the production of ATP. So increasing levels of things like hydrogen ion, potassium ions, adenosine, and prostaglandins, along with carbon dioxide and lactic acid if we're talking about our skeletal muscle tissue. The effects of change in these local conditions or these local chemicals can cause a bunch of different things. So they can cause direct relaxation of the arterioles and relaxation of the precapillary sphincters. They also are going to initiate the release of nitric oxide. And nitric oxide is important because it's a powerful vasodilator. If we're dilating our blood vessels, that means we're going to increase our blood flow, which is what we want because we're showing by having certain concentrations of these chemicals that we're consuming oxygen rapidly and producing waste products rapidly. So if we have an accumulation of the waste products and low levels of oxygen, that means that we need more blood flow there. So we have to dilate our blood vessels in order to increase blood flow. And anytime we have nitric oxide that's being released from our endothelial cells, this can override any type of sympathetic vasoconstriction when those tissues need more blood. We also have something called endothelins. They're also released by endothelial cells, and these are potent vasoconstrictors. So both nitric oxide and endothelins are usually balanced unless our blood flow is inadequate. If we don't have enough blood flow, then we're going to have more nitric oxide release so that we can get more vasodilation and more blood flow to the tissues themselves. Inflammatory chemicals can also cause vasodilation. So myogenic controls, myo means muscle. So when we're talking about a myogenic response, we're referring to a muscle response. So we have local vascular smooth muscle is going to be able to respond to changes in that mean arterial pressure to keep the perfusion constant to avoid damage to the tissue. So yes, we want more blood flow, but we won't want our blood flow to be too high to the point where it's going to damage our capillaries, which remember are only a single layer thick. If we have too much blood flow or too much pressure, it can actually rupture our blood vessels. So we have to balance it. We have passive stretch. This is referring to an increase in our mean arterial pressure is going to stretch the vessel wall more than normal. What's our response going to be is going to basically be to constrict it because, again, we don't want damage. Once it's stretched to a certain point, in order to prevent it from rupturing, we want to constrict it a little bit. And that's going to cause a decrease of the blood flow to the tissue. If we have the opposite effect and we have reduced stretch, meaning that we have a decreased mean arterial pressure, this means that there's less stretch than normal. Our smooth muscle cells are going to respond by dilating to help increase the blood flow to these tissues. Long-term autoregulation. So we have long-term autoregulation that occurs when our short-term autoregulation is not sufficient in meeting the tissue's needs for the nutrients or the gases that it requires. But it can take weeks or months to increase our blood supply. How does it do this? If we're talking again long-term autoregulation, it causes something called angiogenesis. And it's also going to cause our existing vessels to enlarge. So angiogenesis is the process where we are increasing the number of blood vessels in that particular region. So certain chemicals are released that cause blood vessels to want to grow towards that specific area. Tumor cells actually do this. So tumor cells or cancer typically release chemicals that cause angiogenesis or the recruitment of blood supply towards the cancer cells or the tumor itself. Typically that's a bad thing if we're talking about cancer, because what happens is once it recruits the blood supply to that specific area, pieces of the tumor can break off and enter your bloodstream now that it has the blood supply at that particular site. If pieces break off and enter your bloodstream, that can cause cancer to metastasize or be able to spread, because once you're in the bloodstream, you have access to virtually anywhere in the body. Common in heart, if we're talking about autoregulation that's long-term, if we have some sort of blockage in a coronary vessel or throughout the body, or if somebody is in a high altitude. So for some reason you live in Florida and then you all of a sudden decide to move to the top of a mountain, long term, again, it'll take weeks to months to increase your blood supply. We'll see an increase in the amount of blood vessels in your body just so that you're able to meet your tissue's needs for gas and nutrients. So then this is a good little table or image diagram showing you different things that cause either vasodilation or vasoconstriction. So we have metabolic controls that are going to cause vasodilation. So again, we want to increase our blood flow, which is accomplished by dilating our blood vessels if we have low oxygen levels in our tissues, because that means we're using too much oxygen, or we're using more oxygen than our tissues are receiving. So low oxygen would cause us to vasodilate our blood vessels. The reverse is true if we're talking about the metabolic waste products. So metabolic waste products include a high carbon dioxide concentration, high hydrogen ion concentration, high potassium concentration, and then also release of the nitric oxide that we talked about from our endothelial cells, and other things like prostaglandins and adenosine. For vasoconstriction, if we're talking about intrinsic controls, stretch is our major thing. If we can sense that our smooth muscle cells in that particular area are stretched beyond normal, that's going to cause them to constrict in order, again, to prevent damage to those blood vessels. If we're talking about a chemical or metabolic component that causes vasoconstriction, we're really just talking about the endothelium release from our endothelial cells. If we're talking about extrinsic controls, we really haven't talked about those yet, but I'll just point them out now. If we don't have a lot of sympathetic tone, that's going to cause dilation. If we do have a lot of sympathetic tone, that's going to increase constriction. The hormones will hit here in a little bit. So talking a little bit more about skeletal muscle, the blood flow varies with the fiber type and, of course, whatever activity that you're doing. At rest, our myogenic and our neural mechanisms are going to predominate, just to help maintain the blood flow, which is about 1 liter per minute. No, you don't need to know that specific number. Active or exercise hyperemia, this occurs during muscle activity. So the blood flow is going to increase in direct proportion to the metabolic activity that you're actually doing. We have local controls that are going to go in and override the vasoconstriction. And if we override vasoconstriction, that alone can increase our blood flow about tenfold. So again, this is going to occur in response to low concentrations of oxygen and those accumulated metabolic waste products. Okay, our brain. So blood flow to our brain must be constant because our neurons are intolerant of ischemia. So the brain is unable to store nutrients. So we have to always have a very specific blood flow of about 750 milliliters per minute to our brain, regardless of what environment or state our body is in. So one thing we never shunt blood away from is our brain. The control mechanisms are the same twofold that we saw previously for intrinsic mechanisms. We have metabolic and myogenic. So metabolic is our chemical controls. If we have a decreased pH, which means a high acidity, carbon dioxide is an acid, so an accumulation of carbon dioxide as a waste product would be indicating that we have a lower pH than normal. And what those are going to cause is vasodilation. Again, we need more blood flow to that area for increasing the amount of metabolic waste products we have. If we have very, very high carbon dioxide levels, that can actually depress the autoregulatory mechanisms. If we're talking about our myogenic or physical controls, if we have a decreased mean arterial pressure, that's going to cause the vessels in our cerebrum to dilate. The reverse is going to be true if we have an increased mean arterial pressure. That's going to cause them to constrict. Again, the whole purpose of the myogenic controls is really to prevent damage of these blood vessels. So the brain is vulnerable under extreme systemic pressure changes. So we can get something called syncope, which is the same thing as fainting, if our mean arterial pressure in our brain falls below 60 millimeters of mercury. If we get our mean arterial pressure exceeding 160 millimeters of mercury, that can actually result in cerebral edema or swelling. Skin. So back in the integumentary chapter of chapter 1, you learned that skin, one of its functions is as a blood reservoir. So our skin actually holds about 5% of our entire blood volume. The function of the blood that's actually feeding into our skin is threefold. So one of which is it's helping supply nutrients to cells. It's going to be auto-regulated in response to whatever our skin cell needs are for oxygen. Another function of skin is to help regulate body temperature. For example, if our temperature gets too hot, we can sweat to help cool our body. If our body temperature is too cool, we will activate our muscle in order to cause us to shiver to help warm up our body. So homeostasis of our body temperature, our skin plays a huge role. And like I mentioned previously, it holds about 5% of our blood volume, so it is considered a blood reservoir for our body. Blood flow through the venous plexuses below our skin surface, again, help regulate the body temperature, but what actually regulates it is our sympathetic nervous system reflexes, which are going to be initiated by receptors that we have in our skin, as well as our central nervous system. So we already talked about this a little bit, but if our temperature rises from a variety of reasons, it could just be a fever from our body trying to combat an infection, or if we're outside, because again, it's Florida and it gets crazy hot from heat exposure or exercise, what's going to happen is our hypothalamus is going to send a signal to help reduce the vasomotor stimulation of our skin vessels. If we reduce the vasomotor stimulation of our skin vessels, that's going to cause vasodilation. If we're dilating our blood vessels, that means all the warm blood is going to rush into these capillary beds, allowing the heat to escape from our skin. If the reverse is true, if our temperature decreases, we're actually going to take our blood and shunt it deeper where our vital organs are located. And then the blood vessels that lie deep to our skin are actually going to constrict strongly, helping them trap the heat that we have. So blood flow to our lungs, blood flow from our heart to our lungs, and from our lungs back to our heart, that's our pulmonary circulation. Remember, this is a very low pressure, short circuit that we have. So arteries and arterioles are more like the veins and venules if we're talking about pulmonary circulation, meaning that they're really thin-walled and they have a larger lumen. Arterial resistance and pressure are already much lower than the systemic circuit because it doesn't have as far to travel. It's a short pathway. So about 24/10 millimeters of mercury if we're talking about pulmonary circulation. If we're talking about systemic circulation, that was our 120/80 millimeters of mercury. Our autoregulatory mechanisms are opposite. So low levels of oxygen actually cause vasoconstriction. And high levels promote vasodilation. And what this allows is for blood flow to the oxygen-rich areas of the lungs. And that's going to help increase the time allowed for oxygen to be picked up. Okay, blood flow to our heart. That was our third type of circulation that we talked about. Very, very, very short. Circulation called our coronary circulation. And this is going to be influenced by the pressures in our aorta as well as our ventricular pumping. So during ventricular systole, our coronary vessels are compressed and myocardial blood flow is going to cease. So when our ventricles contract, we don't have any blood flow going to our heart itself. It's during ventricular relaxation that the vessels are allowed to for the blood to pass. During the time of ventricular systole, when our coronary vessels are compressed, we do have myoglobin that is stored, and the myoglobin that's stored provides the oxygen needed to our cardiac muscle tissue. During diastole or ventricular rest, the high aortic pressure is going to help force that blood through coronary circulation. In the event that we are in strenuous exercise mode, our coronary vessels are going to dilate, and they dilate in response to local accumulation of various vasodilators. These vasodilators can increase the blood flow 3 to 4 times. Really important because our cardiac cells use about 65% of the oxygen that's actually delivered to them. If we're talking about most of our other body cells, they only use about 25% of the delivered oxygen. The rest remains bound to the hemoglobin and keeps circulating through our body. So increasing coronary blood flow is really the only way to provide more oxygen.